give you guys the rest of the day off and not make you have to use your brains anymore, but no more brains, but there's just too much to cover in this class not to get started today. And I actually made a conscious decision when we were doing somatosensory. Shelley had talked about reflexes associated with the muscle spindle and the GTO in the sensory lecture, even though they were motor, and I thought sensory's hard enough, let's focus on that. So that's really what we're going to come back to today, in addition to talking about things like motor neurons. But we will start with a review of muscle spindles and eventually talk a little bit about GTOs and what they do, in addition to providing sensory information, but how they contribute to movement. So we are starting a sequence of motor. We're going to be talking about different aspects of motor and motor control over the next 4 weeks. And hopefully you picked up a revised schedule. And the only thing that I did, I really did not mess with this very much, but Shelley had taught cerebellum, then basal ganglia, and then upper motor neuron tracts. And your book does upper motor neuron tracts, basal ganglia, and cerebellum. And in my mind, it just made more sense to do it in that way anyway, because we're starting upper motor neurons today. It doesn't make sense not to come back to them for 3 weeks. So the only change really is weeks 9 and 11 flipped. Week 10 will still be basal ganglia. The quickies are going to change in line with what that change is. So just the quickie on week 10, you don't have a quickie next week. The quickie on week 10 will be on upper and lower motor neurons, everything we're covering today. And next week, the week after that, you'll have a quickie on basal ganglia, and then week 12 will be a quickie on the cerebellum. So hopefully that doesn't, if the readings don't change, nothing changes, just we've swapped weeks 9 and 11. Okay? Hopefully really nobody will be angry about that. So today, again, we'll review muscle spindles, GTOs. We'll talk about the difference between upper and lower motor neurons. We're really going to live in the spinal cord today. We're not going to be talking about cortical aspects of movement. That will be for next week. There are 2 types of lower motor neurons that we will discuss and distinguish between. Those are the alpha and the gamma motor neurons. And in the application lecture, we'll talk about motor neuron disorders and sort of aspects that relate to what we might do in occupational therapy. Did you guys talk about upper motor, lower motor neurons in kinesiology at all? Did you talk about fiber types, slow twitch, fast twitch? A little bit? Okay. All right, we're going to do all that today anyway. I just want to see how much of it is going to be reviewed. So, upper motor neurons, they're sometimes referred to cortical motor neurons because their cell bodies live in the cortex, in the motor cortex. The motor cortex is located in which gyrus? Precentral, right, okay. And their axons are either going to travel in synapse in the brainstem, on a lower motor neuron in the brainstem, which would usually be a cranial nerve, or they're going to travel all the way down to different levels of the spinal cord to synapse on lower motor neurons in the ventral horn. So the upper motor neurons, their cell body and their axon are entirely within the central nervous system. And they're going to direct the activity of the lower motor neurons. They're going to tell them what to do and when to fire. And this is going to be mostly important for the control of voluntary movement. We want to move our arm. Our brain is going to direct those lower motor neurons to move our arm in that specified way. Okay? This is what we're going to leave behind today and talk about more next week, what those different descending pathways are from the cortex. Today we're going to live mostly in the world of lower motor neurons. These are sometimes called spinal motor neurons because, again, most of the time the cell bodies are living within the ventral horn of the spinal cord. The exception are those cranial nerves whose cell bodies are in the nuclei of the brainstem. So for example, we looked at the motor nucleus of 5, right? So the cell bodies in there are going to control muscles of mastication. That is a lower motor neuron, all right? But we're going to mainly talk about spinal movements today, so we're going to be talking about lower motor neurons whose cell bodies are in the ventral horn, whose axons form the ventral roots, and whose axons continue continue to travel down and synapse on muscle fibers. So lower motor neurons synapse directly on muscle fiber, and there are two types, alpha and gamma motor neurons, and we'll distinguish between the two of those as we go through the lecture. Just like in our sensory systems, we're going to see a somatotopic organization of the motor system. And this is the first place we're going to see is that the cell bodies of those lower motor neurons, both the alpha and the gamma motor neurons, are going to be arranged in a way that the axial muscles or more proximal muscles are going to be located more medially in the ventral horn. And the distal muscles, for example, of the hands and the feet, are going to be located more laterally in the ventral horn. Similarly, our flexors are going to be located more dorsally to the extensors that are located more ventrally. And so you can see an example of this. If this was the cervical cord controlling aspects of our movement, we're going to see more distal musculature laterally, more proximal muscular medially. Our flexors represented more dorsally than our extensors. And so this really starts to matter when we get back to thinking about disorders. So we talked about central cord syndrome, where there was a degeneration from the central aspect of the spinal cord. What muscle groups are going to be affected first if that degeneration expands into the ventral horn? The axial muscles, so the muscles of the trunk, your postural muscles. What happens if you have an incomplete injury of the spinal cord that doesn't go completely central, but let's say is lesioned about here? You get a knife wound about here. What muscles are most likely to be affected? Your distal muscles, because it's lateral, and in this case the extensors, because we see that this ventral horn comes out and extends all the way to this lateral aspect, okay? So again, we'll talk more about that when we start putting all of the motor stuff together, but somatotopic organization is not something we can leave behind with sensory. We will see it again and again when we talk about motor as well. So again, there are two types of lower motor neurons. I'm going to have to say that slow because for whatever reason it doesn't want to come out of my mouth right when I say it fast. The two types are alpha and gamma motor neurons. Alphas are the stars of the show. They are kind of the big players when it comes to movement. So most of the time when we're talking about control of movement, we're talking about the alpha motor neurons. Alpha motor neurons are going to come down and they're going to synapse an extrafusal muscle fiber. So what we mainly think of as the belly of the muscle, these are the extrafusal muscle fibers. And one alpha motor neuron can synapse on anywhere from like 3 to 1,000 muscle fibers. So if we have an alpha motor neuron, sorry, brachial plexus. We have one alpha motor neuron coming down and synapsing on, let's just say 3 muscle fibers. 1, 2, 3. And we have another alpha motor neuron coming down and synapsing on, let's just say 25 or 250 motor neurons. Synapse, 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 synapse. Which one do you think is going to give us more precision? The one with fewer synapses or the ones with more? Fewer synapses are going to give us more control. We'll talk about that more in a minute. So again, alpha motor neurons are going to synapse on extrafusal muscle fiber, and they're going to generate a contraction of that muscle by releasing a neurotransmitter called acetylcholine. And we talked about acetylcholine when we talked about some of our other disorders like myasthenia gravis and Alzheimer's disease. But basically, the alpha motor neuron releases acetylcholine at what we call the neuromuscular junction. So that synaptic space between the alpha motor neuron and the extrafusal muscle fiber is our neuromuscular junction. Acetylcholine receptors on the extrafusal muscle are going to take up that acetylcholine, and when they do, if it depolarizes the cell, it's going to create an action potential that's going to travel in both directions along that muscle fiber. So again, that action potential is going to travel in both directions along that muscle fiber. And if you remember when we talked about myasthenia gravis, there was a problem with the receptors, the acetylcholine receptors on the muscle itself. So it couldn't take up that acetylcholine, so it couldn't generate strong action potentials, it couldn't generate muscle contraction, and the main thing we saw in myasthenia gravis was muscle weakness, right? So this is sort of putting all of that together. In that case, we're talking about the alpha motor neurons. Two other vocabulary terms that you guys need to be aware of. One is a motor unit. So a motor unit consists of the one alpha motor neuron and all of the muscle fibers that it synapses on. That is one motor unit. And again, you have 3 to 1,000 different synapses. The motor neuron pool are all of the alpha motor neurons that help control a single muscle. So it's like a labor pool. It's like all of the available workers that you have to generate a contraction in that single muscle. So you have a motor neuron pool for every muscle of your body. Make sure you understand the difference between those two concepts. We're mainly going to focus on motor units today and the different types of motor units. Now this is sort of like the picture that I drew up there, only much prettier. But again, a small motor unit is going to have an alpha motor neuron that is going to synapse on relatively few muscle fibers. And you can replace that word cells with fibers, same thing. And that is going to give us good to excellent control of those muscles. So it's going to give us more precision. Smaller muscle units, smaller motor units equal more precision. As opposed to larger motor units that are going to synapse on more muscle fibers, are going to give us relatively less precision and are going to be more for control of like postural muscles. Okay? Does that concept make sense?
So would you see more small motor units in the areas controlling the distal parts of the body, and then more large motor units controlling the extensor parts of the body?
Yeah, it's probably more distributed with small motor units in the distal muscles as compared to the proximal muscles. Great. Another concept of motor units is that motor units, one alpha motor neuron, so again, a motor unit is one alpha motor neuron and all of the fibers that it synapses on. So each motor unit, each alpha motor neuron is going to be associated with one of 3 fiber types. Okay? So fiber type 1 are what we call slow and oxidative. So slow oxidative motor units are related to type 1 or slow twitch muscle fibers. Right? They're always going to be associated. So slow motor units, type 1 slow twitch muscle fibers. These are fibers that generate relatively little force but have a lot of endurance. You're using oxygen as their metabolic process. They have greater blood supply because of this, and they can go for a long period of time. So examples of when we would use slow motor units would be for things like standing, for maintaining a certain posture for a period of time, sitting for a period of time, or sustaining some level of movement. And so the example down here is somebody holding a yoga pose. Okay? On the flip side of slow motor units are our fast motor units. And I'm going to skip over intermediate for a minute. But fast motor units are associated with our fast twitch or type 2B muscle fibers. And these use a glycogen, or process associated with glycolic metabolism, for energy. And this, it's kind of like if you eat a lot of sugar, you go really fast for a period of time and then you completely wipe out, right? So glycolic, muscles that use glycolic metabolism are going to give us a lot of force. They're high in force, they can generate a lot of force, but it's relatively low endurance. So if you think about the difference between somebody coming right off the starting block and sprinting for, I don't know, from here to the exit sign, that's a burst power. It's rapid movements that don't need to be sustained for a very long period of time. And then our third type of muscle fiber are type 2A. These are still considered fast muscle fibers, but they use an oxidative process. They use oxygen for energy, which means they can generate more force than our slow motor units or our slow twitch fibers, but not quite as much as our fast muscle fibers. They also can go longer than fast muscle fibers, but not quite as long as the slow muscle fibers. So they're intermediate. It's moderate. And these are going to be really important for sustained locomotion. Right? So again, it's the difference between I think this is Usain Bolt coming off the starting blocks, and somebody running a marathon or running cross country. They have to be able to sustain that for a long period of time. They're going to use a different type of muscle fiber. Right? So the question is, often, can we change our muscle fiber type? The research on this is N. Now, most muscles contain about 50% slow twitch and about 50% fast twitch. Okay, that's the average, but we know there's differences in all of us. We know that within fast twitch types, if you have somebody like my son who's very fast, naturally fast, has a lot of, I think, 2B muscle fibers, I haven't tested that, but I'm pretty sure. And you make him go running with you and run for 3 miles or 5 miles every day for a period of time, which his mother made him do when he was younger. Then what you might see is some of those fast twitch muscle fibers transitioning over to intermediate type fibers. So they don't change necessarily in their inherent properties, but they do change in the type of metabolism they're using. So they become better at endurance. They become more efficient. They can go for longer periods of time. So that's one change that we know can happen, is that you can train your muscles to change from a fast twitch type 2B to a fast fatigue resistant type 2A. We also know that type 2B fibers, to sustain them and to strengthen them, you need continual exercise. That without resistive work, without some type of force, without using them, they're going to be more prone to atrophy. So again, somebody like my son that might have a lot of these fibers, if he's never sprinting, if he's never running and using those muscle fibers, they are more likely to go away compared to, or to atrophy, that compared to the slow twitch muscle fibers or even the intermediate muscle fibers. And this can be important in terms of OT because these fast twitch muscle fibers allow us to perform really rapid movements. And so, for example, in the elderly who maybe are not doing some type of resistive exercise on a regular basis, they're going to be more prone to lose their fast twitch fibers. And then they trip and they need to rapidly extend their arm to catch themselves, and they're less able to do that. Their ability to move their muscles quickly becomes diminished, they're slower in their reaction times, and they're going to be more likely to have an injury due to fall. So when we think about working with people who have atrophy or their muscle function has declined, sometimes we do use strengthening programs to try and target these fast twitch type muscle fibers. And we'll talk about that a little bit more in the afternoon. Yeah, yes, sir.
So the fast twitch, they have high force. You don't necessarily have to be moving fast to use them. You just need to have some resistance, basically, enough to recruit them.
Either resistance to recruit, yeah. So we'll look at, can you hold that for a second and see if the next slide answers that question? So these are going to be used when we need to generate a lot of force. So either force against resistance, like lifting a heavy weight, or force against gravity, or some type of burst of power in our speed of movement. Okay. But there is a diagram that I think will help with that too. So there's two different principles on how these motor units get recruited. And the first is called the size principle. And don't get this confused with necessarily the size of the motor unit. So we're not talking about how many synapses are on the muscle fiber we're talking about the diameter of the muscle fiber, because type 1 fibers tend to be a smaller diameter compared to intermediate fibers, compared to type 2B fast twitch fibers, okay? So that's why this is called the size principle. And the principle basically states that motor units are not recruited at random, that they are recruited in a specific sequence, in a specific order. And that order is that type 1 fibers are recruited first because they are the least likely to fatigue. If more force is necessary, then we start recruiting intermediate type fibers and or type 2B fast twitch fibers. This is the sequence. Even if you're talking about Usain Bolt and you know you're going to need to use these type 2B fibers, the recruitment starts in order from type 1 to type 2B. So we can look at this. Here. So here, again, these are related to the size. So here's our type 1, here's our type 2A, here's our type 2B fibers. And you'll see when I hit play that you're going to see recruitment in that sequence. And I'm going to play it a second time, and I want you to watch how the forceometer moves in terms of how these are recruited. So we'll do it twice. Type 1, type 2A, type 2B. So we'll watch it one more time. And this time, watch it in association with the force. More force, max force. Okay? Does that make sense in how they're recruited in that order? Okay. The website's good. If it's not making sense, that website, that link, it's the same link that I have here. So if you need to see it again, go back and take a look at it. Yes.
You might have said this, but if you're doing like a sprint, even if you don't need the type 1 in what you're doing,
They're still going to be
they're still
active.
recruited.
Yep.
So,
Yep.
Would the length just be shorter? Would you jump faster to type 2?
Yes, good point. So with that case, if you're going right off the starting blocks into a sprint, you're going to get to that type 2B a lot faster than you would be if you were running cross country. If you're running cross country and your muscles start to exhaust, you're going to start recruiting all the motor units that you can. But you're going to get to that point much slower than if you were coming off the sprint. That's a good question. Okay, so that's one. The size principle is one principle or one way motor units get recruited. The other is the rate code, and the rate code states that as there is an increase in action potentials fired, that alpha motor neuron increases the amount of force on that motor unit can generate. So it increases the number of action potentials or the firing to that muscle, which is going to increase the rate or intensity of muscle contraction. So again, let's take a look at this site. 315. So there's going to be 3 different scenarios, and in the first scenario, what you're going to see is a single action potential fired. So you'll see the green line blip, and you'll see a commensurate amount of muscle force generated. And you can watch that here, and you can watch it on the forceometer. The muscle's going to go back to a resting state, and then another action potential is going to be fired. And you'll see that same amount of force be generated. So it's 1 equals 1, 1 equals 1. Okay, so the one action potential is going to deliver X amount of force. And if the muscle goes back to rest and that same action potential fires again, that same amount of force is generated. Now, if these action potentials occur close together, they can be summated or added together, which is going to result in more force than any single action potential occurring alone. Okay, so let's take a look at that in number 2. So you have a couple that occur together, and you're going to get more force because of the summation of those action potentials. And then as action potentials continuously fire, we get to the point of max force. And the maximal contraction a muscle can deliver, the maximal amount of force is called tetanus, okay?
This was all within one motor unit.
All within one motor unit, right. And so, it's a good point, Dustin, is that the more motor units that are recruited, again, this is just looking at one motor unit, each muscle is going to have a pool of alpha motor neurons to draw from, and so you're going to have not only summation of action potentials within one alpha motor neuron, but across those different motor units, so that the more motor units that are firing, the stronger that contraction is going to be. Yeah.
Is this, so with this, are these supposed to be combined together, or is it like, this is a separate principle from the first one? Because this is talking about any type of, any size,
Yeah, so these two principles, the size principle and the rate code, are always sort of active at the same time.
Okay,
So
so
you're
they're not
always,
opposing
no matter how many action potentials are being fired, you're always recruiting from type 1 to type 2
Okay.
fibers. You're always gonna have this summative effect of the more action potentials that are being fired, the greater that force is gonna be.
I don't know if I know how to ask this, but like say you were contracting and holding for a long time, does that have anything to do with, would that just mean you have action potentials firing continuously?
Yes. So if you're contracting and holding, you're gonna have continuous action potentials fired, but I'm gonna pause the rest of that explanation for the afternoon, because we're gonna be talking about isometric versus isotonic contractions. Okay, so, all of that was to say what alpha motor neurons are kind of going out and doing at the muscle. We'll stop briefly to talk about who is talking to that alpha motor neuron, okay? And there's three sources of input to the alpha motor neuron. One is that input from the brain, from upper motor neurons, can come down and synapse on those alpha motor neurons in the ventral horn of the spinal cord. So that is one source of input, upper motor neurons. Another source of input that we're going to look at more closely is input from the muscle spindle itself. So the muscle spindle is type 1A fibers. They're going to come in through the dorsal horn, and they're either going to synapse directly on the alpha motor neuron, or they'll synapse on an interneuron, which is our third source of input, that is going to communicate directly with the alpha motor neuron. Upper motor neurons can also synapse on interneurons before hitting the alpha motor neuron. But the three types of input, the three synapses that you might see on the alpha motor neuron, the upper motor neurons, information from the muscle spindle, those type 1A fibers, and interneurons in the spinal cord. So let's go back and refresh your brains about muscle spindles. Muscle spindles are located within the muscle, and in this picture the muscle spindle looks pretty big compared to the extrafusal muscle. In reality it's more like this, and there's more than one muscle spindle per muscle. But we'll use this picture because it's bigger and it's easier to see. The muscle spindle itself contains what is called intrafusal muscle fibers. So these pink fibers here, right, are intrafusal muscles. And those muscles, intrafusal muscles, have the sensory fibers, those type 1A fibers, wrapped around them, so that the sensory input coming from the intrafusal muscle fiber is going to give us information about what? What do muscle spindles give us information about? Muscle length. And we say sometimes they're called stretch receptors because as the muscle itself stretches, the muscle spindle stretches. They give us information about muscle length. Now we'll come back to this concept in a minute, but the muscle spindle also gets motor innervation. So those intrafusal muscles also get motor innervation. They aren't just sensory receptors. And that motor innervation is going to come from gamma motor neurons. So alpha motor neurons synapse on what type of muscle fiber? Extrafusal muscle fiber. Alpha motor neurons synapse on extrafusal muscle fiber. Gamma motor neurons synapse on intrafusal muscle fibers that are in the muscle spindle. So the first, we're not doing pathways today, but we're gonna be talking about reflex pathways. So it's sort of pathways are a little more simple than what we typically are used to. So the first reflex we're gonna look at is called the stretch reflex or the quick stretch reflex, sometimes called the myotatic reflex. Myo meaning one, there's only one synapse here. So this is a monosynaptic reflex. And the connection is between the 1A sensory afferent coming from the muscle spindle, synapsing in the ventral horn of the spinal cord on the alpha motor neuron, which goes out to innervate the extrafusal muscle fiber. And so here is an example. I'm going to go through one example, this picture of what the stretch reflex looks like, and I'm going to play a video that goes through a second example. And so you'll have that if you need it. So in this example, quick stretch is going to be caused by a weight. Quickly, suddenly, this is the quick stretch reflex, suddenly being dropped into the hand. Okay? When that happens, the muscle is going to lengthen because the muscle is going to give to be able to catch that sudden weight. And so in this example, we see a lengthening of a biceps muscle. And that is going to stimulate the muscle spindle to send an action potential down the 1A afferent and depolarize our alpha motor neuron. And so the alpha motor neuron is going to be excited. It's going to go, we need to do something, and it's going to tell that extrafusal muscle fiber on the biceps to contract, and the response is contraction of the biceps to meet that weight, to generate an equal or greater amount of force to that weight, to that resistance. Yes. So in this example, we have a quick stretch that is caused by weight being dropped onto the arm, onto the hand. It's causing a lengthening of the bicep muscle. So it's eliciting a lengthening of the muscle spindle, which is going to depolarize that 1A afferent fiber, which is blue in this diagram. That is going to synapse on our alpha motor neuron. And the alpha motor neuron is going to go out to the extrafusal muscle fiber on the bicep and tell it to shorten or contract to meet the force of that resistance. So that's the third picture. You see the arm holding the weight. Okay, so it's the difference. This is a reflex. Again, it happens quickly. So it's the difference between you're at the gym and somebody tosses you a 25-pound dumbbell that you have to try and catch really quickly versus you consciously going to pick a dumbbell up. Okay, so we're talking about a reflexive pattern here. Let's go ahead and watch the video because this is going to go through sort of your more traditional stretch reflex that you would test by tapping the knee. And if you guys have questions after that, I can answer them.
Okay, the first specific reflex we're going to talk about is the stretch reflex. This is a somatic reflex. It is monosynaptic, meaning that it will only require a sensory neuron and a motor neuron without an interneuron. This particular image is showing an example, a diagram of the stretch reflex. The first component here is the stretch receptor. This is called muscle spindle. It is a sensory receptor that detects stretching in the particular muscle. When the muscle is stretched, for example, when a reflex hammer, like you see here, taps the patellar ligament, it creates a stretching in the muscle that will stimulate the receptor, which will then create a nerve impulse along the sensory neuron. Now it does this in the typical way. Mechanically gated ion channels will open in response to the stretch, depolarizing the membrane, creating a gradient potential. If the stretch is strong enough and enough ion channels open, the gradient potential will reach threshold, a voltage gated ion channel will open, resulting in an action potential or a nerve impulse along the sensory neuron, as you see here. Sensory neuron will travel back up the femoral nerve, in this case, or whichever nerve innervates the muscle in question, and is going to travel back to the spinal nerve, into the dorsal root ganglion, into the dorsal root of the spinal nerve, into the spinal cord via the dorsal horn of gray matter, which you see here. Then we'll travel along this path right here, where its synapse is immediately a motor neuron. That motor neuron will take an impulse and continue the impulse through the ventral horn of gray matter, which you see here, out the ventral root, out the mixed spinal nerve, and back along that motor neuron to the same muscle. And will stimulate it to contract, which will counteract the stretching to protect the muscle from an overstretch. This reflex is monosynaptic, meaning that there's only one synapse to have the reflex control. It is ipsilateral, meaning that the motor impulse leads on the same side of the spinal cord. And it is not intersegmental, meaning that the motor neuron is also on the same segment of the spinal cord as the sensory neuron. Now, the dotted line you see here and the extra branch you see here is what's called the reciprocal innervation. While this reflex is going on, another impulse is branching off from the sensory neuron that is going to stimulate an interneuron in the integrating center. This is the integrating center of the reflex arc. This is the integrating center of the reciprocal innervation. This interneuron is inhibitory, which means that it will synapse with a motor neuron, inhibiting it from firing a nerve impulse. That's why it's a dashed line. There is no impulse traveling along this motor neuron. This motor neuron innervates the hamstring muscles, which are the antagonist of the quadriceps. If this motor neuron is inhibited, it will prevent the hamstring muscles from contracting. What that does, that makes it easier for the quadricep muscles to contract because the opposing muscle is forced to relax. Each reflex has a reciprocal innervation. The reciprocal innervation will typically do the opposite of the reflex in the antagonistic muscles, making it easier for the reflex to take place.
Okay, and that's what we're going to talk about next, is reciprocal innervation or reciprocal inhibition. So just to summarize the stretch reflex, we have a quick stretch to the muscle. Do a quick stretch to the muscle that activates the 1A afferents. They're going to then activate the alpha motor neuron in the spinal cord in the ventral horn. The alpha motor neuron will send an efferent signal out to the extrafusal muscle fiber. That extrafusal muscle fiber will contract, increasing muscle tension and opposing the stretch. So that reciprocal innervation that you saw is outlined here. And basically when we're talking about reciprocal innervation or reciprocal innervation, muscles on one side of the joint are going to relax to allow greater contraction of the stretched muscle. And so it's that balancing of agonists and antagonists. And so it doesn't only occur, the example they showed was hamstrings and quadriceps. We could see it in biceps and triceps or other groups that have opposing muscle groups. So as one is being facilitated or encouraged to contract, the other is being inhibited through that inhibitory interneuron. And so is this something we can use therapeutically? And to demonstrate that, I'm going to make you guys all stand up. You guys did some gym work over spring break. What I'm going to ask you to do is first reach up to the ceiling, get somewhere that you can touch your toes. So I want you to lean down and just try and touch your toes. Kind of see how far you go, don't push it, just see what your natural stretch is. Come back up. Now I want you to squat. Get as low as you can go and hold it. Feel the burn. You should be feeling the burn on your quadriceps. Come on, I'm an old lady. You guys should be able to hold this longer than me. stand up, touch your toes again. Easier that time? It should have been, especially if I made you hold that position longer. Because you guys can go ahead and sit. As your quadriceps are having to contract, you're getting that reciprocal inhibition to the hamstrings. They're being told to relax, to not fire. So that relaxation of the antagonist can help actually with stretch and flexibility the next time you go down. So when you're learning different stretch patterns or exercise patterns in your adult classes, we don't do this so much with kids. You can think about what you can do, what muscle groups you're trying to stretch, and then what exercises you could do to help encourage stretch or use this principle.
Is this at all related to like tapping or something like that, where you're giving them like a tricep feedback or something like that, where it's like you're tapping and something to give them a stretch reflex?
So yes, so it doesn't necessarily relate to reciprocal inhibition, but if you're tapping on the muscle, you are activating that quick stretch reflex to try and get that muscle to contract. Yes, absolutely. Sorry, yep.
So I understand the muscle stretch reflex where you put the weight, like catch a weight and it stretches it, but how does like tapping the knee activate the spindle? Like where's the stretch?
It's causing a stretch in the tendon that is pulling on the muscle.
Okay.
If you go back and look at the video, I don't have a picture of it to show it, but by tapping on that tendon, you're stretching the tendon, and that's going to pull a stretch on the muscle. Yeah. And you can do the same thing with the biceps. You know, if you tap the tendon here, it's going to cause the stretch in the muscle. It's short, but it's quick enough that it's going to elicit that reaction. Leah.
Is it that way for all muscles or just tendons or? The only reason I ask is like it's for me people with get behind the block and where they like slap their bodies and muscles and I never knew why. I don't know if it was a high pain or if it was if people were like, yeah, it helps me sprint better. I'd be like,
Yeah, I don't know the answer to that. I mean, yeah, in terms of actual enhancing performance, I don't know. I mean, like Dustin said, that the tapping, you're trying to elicit the stretch so that muscle will independently or voluntarily contract. I don't know about what the long term, if you're going to be swimming and you're tapping, I don't know the answer to that.
I just thought I would ask.
Okay, let's switch gears again, just to give you a frame of reference. We have upper and motor lower neurons. In terms of lower motor neurons, we have alpha motor neurons, and we have, wait a minute, I already did this, didn't I? Gamma motor neurons? Did we not talk about gamma motor neurons? I'm sorry, we talked about muscle spindles, sorry. Lost my train of thought, I'm thinking about swimmers, slapping myself. Okay. All right, gamma motor neurons innervate the intrafusal muscle. I did say that really quickly. And they innervate the spindle ends. So if you look at these intrafusal muscle fibers within the muscle spindle, our green gamma motor neurons are only synapsing at the ends of these muscle fibers. And they are going to, activation of the gamma motor neuron is going to cause the ends of the spindle to tense or to lengthen, okay? Well, they're going to contract, but it's going to cause these parts of the muscle spindle to tense. And I'm going to show you that on the next slide. What they do, their purpose, and again, I'm going to explain this better on the next slide, but just so it's out there, what the gamma motor neurons exist to do. Again, alphas are sort of stars of the show. The gamma motor neurons exist to keep the 1A afferent active, so that the muscle spindle is continuously able to send input to the central nervous system. And that process is called alpha-gamma coactivation. So again, the purpose of the gamma motor neurons is to maintain that spindle sensitivity, to allow it to continue to send input via that 1A afferent, even when the muscle is contracting or shortening. So let me walk you through that. In this picture, we have extrafusal muscle fiber here that's going to be innervated by our alpha motor neuron. We have our muscle spindle here with our intrafusal muscle that's going to be innervated at the ends by the gamma motor neuron. And then we have the 1A to detect changes in length and send that information back to the central nervous system. Are we clear on that part of it? That's sort of baseline. Okay? Now, as that muscle, as that alpha motor neuron sends a signal to the extrafusal muscle fiber, that extrafusal muscle fiber is going to contract and it's going to shorten. And that's good. We expect that to happen. But if that muscle spindle also kind of becomes floppy and shortens, you can see the ends there are wiggly, then the 1A afferent, that orange one, the sensory neuron, goes offline. It stops sending signals to the brain. Okay? So if that muscle spindle, if those ends don't stay taut, and it shortens and becomes wiggly, that 1A sensory afferent can't send information about muscle length to the brain. So you see in this example, the alpha motor neurons firing, you got nothing coming from the gamma, and the 1A afferent can't send signals back out. So this is not normal. What happens, or what allows this not to happen, is that we get co-activation of the alpha and the gamma motor neurons. So they're activated simultaneously, so that as that alpha motor neuron comes in, causing that extrafusal muscle fiber to shorten and contract, the gamma motor neuron is also firing, and it's telling those ends of the spindle to contract and stay taut. And that allows that 1A afferent to stay online and keep sending signals about muscle length back to the brain.
Can you explain the difference between B and C again?
Sure. So in B doesn't really happen. So, okay? But B is what would happen if we had activation of the alpha motor neuron without activation of the gamma motor neuron. So what would happen is we would have that extrafusal muscle contraction, shortening the muscle, but without the gamma activation, these ends would become slack, and the 1A afferent would stop firing. Okay? What does happen, hopefully in all of us, is that as your alpha motor neuron contracts and causes shortening of the muscle, we get a co-activation of the gamma motor neuron, which tells the spindle ends to contract and stay tight, and that allows the 1A afferent fiber to keep sending signals about muscle length back to the central nervous system. Okay? So again, the whole purpose, the existence of gamma motor neurons, is for this purpose, to make sure that the 1A afferents can keep doing their job. Good with this? Okay, I told you you weren't allowed to forget about muscle spindles or Golgi tendon organs. Those are our GTOs. GTOs are our other type of proprioceptors that are located within the muscle, and they're really located at the junction between the extrafusal muscle fibers and the tendons. So they're located here, and they would be located down here. And GTOs give us information about muscle tension. Okay? Muscle tension comes from Golgi tendon organs. And the purpose of the Golgi tendon organs is really to protect our muscles from overstretching and to help us maintain a optimal tension within the muscle, particularly when we're using the muscle. So when we talk about grading force, the GTOs are going to help us with that. So they're going to help us grade our tension on a regular basis and also protect our muscles from overstretching if there's too much tension. And here's how GTOs work. Okay, ready to look up? So, if the muscle begins to stretch, you're going to have tension on the tendon. It's going to activate the Golgi tendon organ. It is going to still follow that same pathway that the muscle spindles, the 1A afferent fibers travel. What type of fiber is this? It's not 1A because that was muscle spindles. 1B, type 1B fibers coming from GTOs. So these 1B fibers sensory axons are gonna come in the dorsal horn. They're gonna synapse on a interneuron, and this is gonna be an inhibitory interneuron, because that interneuron is going to stop, see the minus sign, the activity of the alpha motor neuron, so that alpha motor neuron stops firing. So in the case where you have excessive stretch of a muscle to the point where there could be damage, the GTO is going to fire rapidly and say stop, 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 danger, danger, danger. It's going to inhibit the activity of that alpha motor neuron so that it stops telling that muscle to contract. So it reduces the tension. In normal functioning, again, the GTOs just exist to help regulate our force and regulate pressure, so that as we are picking up a fragile object, we have to grip it hard enough so that it doesn't slip through our hand. But if we grip it too hard, it could shatter in our hand or break off. Same thing when we regulate our force picking up a juice box, okay? If we don't pick it up with enough force, it's gonna slip out. If we squeeze it too hard, then juice is gonna squirt out of our straw and get all over our sandwich, and then we'll be sad, okay? So GTOs exist to help regulate muscle tension, muscle force through this polysynaptic inhibitory process. Polysynaptic because there's an interneuron there. Lars?
So that's the pain I feel in my hamstrings, like my toes, is that?
Yeah, that's coming from pain receptors and free nerve endings in your muscle. But yes, the tension is being communicated by your GTOs, saying stop now, all done, this is as far as you can go. Speaking of pain, our next reflex is mediated generally by pain receptors. Don't get too distracted by that animation. Sometimes I forget that they do that. The flexor withdrawal reflex is a safety reflex. When we, in this example, step on a tap, we need to be able to flex our muscles to be able to withdraw our leg or our foot from that painful stimulus. This reflex works when you touch a hot stove, so temperature pain receptors. You want to withdraw your arm from that stimulus. It's a flexor response. It can be stimulated even by light touch, which we don't typically think of as painful, but if it's an overstimulating, uncomfortable light touch, like a butterfly or something fluttering against your arm, you're alarmed and you pull it away. So this reflex is dependent on how painful the stimulus is. It's going to be a faster reflex if it is more painful, the greater the intensity of the pain. It's also going to be dependent on the direction of the stimulus. So your withdrawal is going to be away from wherever the stimulus is located. And I'm going to let YouTube walk you through this reflex, but I'm going to point out a few things before we go. First is that it's going to start, it's polysynaptic, it's going to start with the sensory afferent, so the pain fiber. Pain is carried along, I feel like I'm torturing you guys today, but what type of fibers? A delta and C fibers. Okay, so those are going to come into the dorsal horn, and in this case, remember sometimes with the spinothalamic tract, it ascends or descends a few units before doing its thing. And so what we're going to see here in this reflex is that it may come in and synapse at the same level it enters, but it also may ascend and descend a few spinal cord segments in order to activate all of the flexors that you need to pull your arm away from that stimulus or pull your leg away from that stimulus. The second synapse, or well, the first synapse, this neuron is going to come in and synapse on an excitatory interneuron. So the interneuron is excitatory because it's going to excite the alpha motor neurons that it synapses with. And those alpha motor neurons are going to stimulate the muscle to flex and withdraw. So that's the basis of the reflex. Let's go ahead and have somebody else walk you through it. And again, you can come back to this anytime.
The next reflex we're going to talk about is the flexor reflex, also known as the withdrawal reflex. This is a reflex that is polysynaptic and is protect you from a potentially harmful stimulus. In this particular instance, what we're seeing is that in this picture, this individual has stepped on a tack. That is going to stimulate sensory receptors, and this.
Let me orient you real quick, I apologize. Here's what confused me the first time, and I know you guys are infinitely wiser than I am, but just in case. This is the same leg. Okay? Alright? So he steps on the tack. This is just they're both the right leg. He's stepping on the tack here, and this is showing what's going to happen to that leg. Okay? It helps to know that before going into this.
Sensory receptors in this particular reflex are nociceptors. These are pain-sensitive receptors. So tissue damage is the stimulus, which would result in your brain perceiving it as pain, that causes this reflex arc to initiate. So let's follow the reflex arc. As the foot steps on the tack, it's going to stimulate the sensory receptors, generating a nerve impulse in a sensory neuron that will travel into the spinal nerve, in the dorsal root, in the dorsal horn of gray matter, and branch and synapse twice. Now these two synapses are unique because, first off, one of them will stimulate the contraction of a specific muscle. One branch is synapsing with an interneuron, an excitatory interneuron, that will then synapse with a motor neuron. What that is resulting in is the motor neuron impulse coming out the ventral horn, actually the ventral horn of gray matter and the ventral root, and then out the spinal nerve and to the hamstring muscle, causing it to contract, which will flex the knee, pulling the foot away from the stimulus. Why it's called the flexor, because it flexes the knee, or the withdrawal reflex, because it withdraws the body part from the stimulus. So that's one thing that's happening here. Another thing that you're going to notice is that different parts of the hamstring muscles are innervated by different levels of the spinal cord. So different nerves are innervating the hamstring muscle group that can be traced back to different spinal nerves. So one of the branches that's going to synapse here is going to synapse with an interneuron that will then travel to different segments of the spinal cord, maybe one level up and one level down in the spinal cord, where it will then synapse with an interneuron, an excitatory interneuron, that will synapse with a motor neuron at a different level, which will also exit the spinal cord, go through the ventral root into the spinal nerve, and innervate a different section of the hamstring group. So because the hamstring muscles need to contract for this reflex arc, and the hamstring muscles are innervated by different levels of the spinal cord, all those levels of the spinal cord have to be stimulated to finish the reflex arc on the motor end. So this reflex is termed an intersegmental reflex arc, because not only is it resulting in the stimulation of a motor neuron at the same segment, but it also will use interneurons that travel superiorly and inferiorly within the spinal cord to then stimulate motor neurons that exit the spinal cord on different spinal nerves at different levels of the spinal cord, maybe L1, L2, L3, etc. So this is a polysynaptic reflex arc because it requires multiple synapses, and it's an ipsilateral reflex arc because the same muscle contracts on the same side of the stimulus. And it's also an intersegmental reflex arc because it requires the stimulation of motor neurons that come from multiple sections or levels of the spinal cord. This reflex image here does not depict it, but this reflex will also have reciprocal innervation, causing inhibitory signals to go to the quadricep muscles, turning them off so that the hamstring muscles can contract more easily. Very typical reciprocal innervation. It is just resulting in the opposite effect to the antagonist. That is.
Okay. So again, the main reflex arc is going to cause flexion, but you will have reciprocal innervation to the extensors to relax them so that you're not fighting against that extension. Now that is a little bit different than what we're going to talk about on this last slide, which is the crossed extensor reflex. And this is what's going to happen. This is only going to be in the lower extremities. We're going to take that same example of stepping on a tack. You guys can look up for a second. I don't know how well you can see me, but if I'm stepping with my right leg, which was what the other example was, and I go to step on that tack, right? Where is my left leg? Off the ground. So something is going to need to happen with this leg so that as I bring this leg up, I don't fall over. Okay? So again, as I get a painful stimulus here and I need to withdraw this leg and bring it up, I need to have something happening on the opposite side of my body so that I can withdraw my leg from that stimulus. And that thing that happens is the crossed extensor reflex, where, again, it's another polysynaptic reflex, but that initial sensory input, that initial painful stimulus is going to synapse on an interneuron that's going to cross over in the spinal cord and activate alpha motor neurons that are going to stimulate extensors in the opposite leg. So again, one leg needs to flex up and withdraw, the other leg needs to extend to maintain balance and to compensate for that flex or withdrawal. And you will also have reciprocal inhibition of the opposite side, so that as the left leg is extending and you're activating those extensors, you're going to be inhibiting the flexors. So let's go ahead, it's the last thing today, let's go ahead and watch that loop.
Last reflex I'm going to cover is the crossed extensor reflex. The crossed extensor reflex happens in conjunction with the flexor or withdrawal reflex. And the reason why it happens is because, as you can imagine, if you are going to flex your knee and pull your foot up off the ground to avoid the tack you just stepped on, you're also going to have to balance yourself on the other leg so you don't come tumbling to the floor. So the crossed extensor reflex is exactly what it says it is. It is going to result in stimulating the extensor muscles on the other side of your body, or in the other lower limb. That's the crossed extensor reflex. So the interesting thing about this one is it uses the same sensory part of the arc as the flexor or withdrawal reflex because it is being stimulated by the same tack. So let's look at this image here. We see again, here is the foot. This is actually where the foot begins. This is where the foot ends. So these two pictures are the same leg. This is showing you when the stimulus happens, and this is showing you what the result is going to look like. Okay, so this is the same leg showing you the motion. On the opposite side, we see the other leg, on the contralateral leg, and this is where the leg may have been in your stride when you stepped on the tack, and this is how the leg is going to have to end up as a result of the cross extensor reflex, because it has to stand up and balance you on that leg while the other leg is off the ground trying to withdraw from the tack. So again, let's start with the sensory stimulus. The tack stimulates the nociceptors on the right foot, let's say, and that generates a nerve impulse in the sensory neuron. The sensory neuron nerve impulse travels along this blue line, that's the sensory neuron, into the spinal nerve, through the dorsal root ganglion, into the dorsal root of the spinal nerve, and into the dorsal horn of gray matter. Now, we saw already with the flexor or withdrawal reflex that it then synapsed with interneurons, one that came out the same section, like you see here, through the ventral horn of gray matter, through the ventral horn of the spinal cord, out the spinal cord, and then other synapses that ascended or descended to separate segments of the spinal cord so that they can continue to stimulate the whole muscle group, even though some of those innervations come from different segments of the spinal cord. That we saw already in the flexor withdrawal. Now, what we didn't see in the flexor withdrawal is that the interneurons that are synapsed by the sensory neuron in the flexor withdrawal reflex, some of them are going to cross the midline of the spinal cord and then exit the spinal cord on the opposite side, the contralateral ventral horn of gray matter, like you see here, and synapse with a motor neuron coming out of the ventral root, out of the spinal nerve, and to the contralateral quadricep muscles. Now, because different segments of the quadricep muscles or different extensors in the thigh are going to need innervations from different segments, we also have interneurons ascending and descending the spinal cord so that they can stimulate motor neurons from different divisions or different segments of the spinal cord. So now what we have is motor neurons being stimulated, causing contraction of the contralateral quadricep muscles and other knee extensors. So that way, the body can balance itself on the opposite leg, while the ipsilateral leg is being withdrawn from the harmful stimulus. This
And again, we would have reciprocal inhibition, in this case of the hamstring, so that the extensors can do their job.